Hello, my name is Ted Shepard. I'm at the University of Reading in the Department of Meteorology. And I was asked to talk about how will global and UK climate and hazardous weather change in a 3 degree or more world. So the first thing to say is it's going to get hotter. The map on the lower left here shows the projected changes. This is the average changes over the climate models by the end of the century under RCP 8.5, where it's 4 degrees of warming, global mean warming at the end of the century. And the stippling here indicates the models agree on the sign that it will get warmer everywhere on the planet. And this warming is increasingly obvious to us. It's in our face. This is a paper actually from now 10 years ago, which is very nice, which used the 500-year record of temperature from proxy data. And by adding 10 years onto the 500 years, the map here, the map shows the colors show the decade of the hottest summer. The red colors show the current decades, and you can see that the map changed dramatically with just adding 10 years to a 500-year record. That cannot happen by chance. This is clearly showing that there's climate change going on, and it would be really nice to see this map updated to the present day, since we've had some extremely hot summers in the last 10 years. So actually, single events are often now telling us that we have climate change. But statistically, we think of climate change as a change in the frequency or the likelihood of weather conditions. Here in this cartoon, I've just shown as a pair of Gaussian distributions, which are shifted, so it's very idealized. P1 is the distribution with climate change. P0 is the distribution without climate change. So the effective climate change is the difference of the two. You can just think of, let's say, temperature and things getting warmer. So in the case of a small shift, shown here, for example, these gray lines, you see a small shift in the extremes, and you can either characterize it as a change in the frequency for a given magnitude or a change in the magnitude for a given frequency. This is the way it's often done. And these shifts are small in magnitude, but they can very much matter for climate impacts, of course. But in the case of a large shift, which is what we're increasingly getting, of course, but then it's a bit of a different situation, because what used to be extreme, for example, the vertical solid line here, which was really in the tail of the distribution P0, is now in the center of the distribution P1. So what was extreme is now normal, and the conditions are without historical precedent. So in this case, representing climate change as a change in likelihood, for example, through risk ratio, would be very misleading. For example, a rare heat wave shown in the solid line here, for example, in the P0 distribution, would be really in the tail and would have to be associated with unusual dynamical conditions such as atmospheric blocking. But it would just be in the middle of the distribution, so it wouldn't be unusual at all in P1. So blocking is a compound event which affects precipitation, affects air quality, and so on. And the impacts, of course, very much depend on these compound events. So if the dynamics of the weather conditions didn't change, then what we could do is we could imagine the same extreme events in a warmer world by imposing the conditions in a climate model together with the warmer ocean temperatures and increased greenhouse gas concentrations to fill in what the climate scientists would tend to call the physics, things like moisture. This has actually been done in the regional climate modeling community for a long time, originally done to overcome the biases that exist in climate models and still exist, called the pseudo-global warming method, which is a very unfortunate term, I think. More recently, it's been used in extreme event attribution, where it's called a storyline method. And the advantage of this method is it builds in what we know with confidence about climate change, which is the warming of the ocean and the increasing greenhouse gases. And what it can tell you and quantify is things, for example, that heat waves over continental regions should intensify faster than global mean warming because of land surface feedbacks. So this is exemplified in two recent studies, one from my own group, where we looked at the Russian heat wave in 2010, and this is a time series. These are days of the month. So the early August, late July, early August of 2010 was the maximum heat wave, and you can see it's well above the climatology in that part of Russia, and the heat wave was made at least two degrees warmer by climate change compared to a global mean warming of about 0.7 degrees in this calculation. This is a different study from the ETH Zurich group looking at the 2018 summer, which of course was a heat wave in Northern Europe and Central Europe. And you can see that the black line here is the global mean, it's showing the ratio between the global mean warming and the extreme temperatures. And you can see that when you nudge to these observed state, it's increasing at a much steeper slope relative to global warming. But of course, the dynamical conditions certainly could change. And it's this that represents a major source of uncertainty in climate change, in climate information for adaptation. And it's fair to say that in general, such changes are not well anchored in accepted theory, unlike the thermodynamic changes, are not detectable in observations, and are not consistently represented in climate models. Where they are, it's only in the zonal mean, and which is not too informative at the regional scale. So even for the case of, let's say, wildfire, which is usually considered a poster child, if you like, of climate change, the 2019 Australian wildfire was a very serious season. This is an analysis led from the Australian Bureau of Meteorology, where they looked at the change in the fire risk. This is a fire risk index, which is an empirical index made up of temperature and precipitation that's not known to lead to a higher likelihood of forest fire. And they looked at so you can see that the risk increased a lot over historical conditions over southeast Australia in that period. But the contribution to that increased risk from the trend part, which is the long-term warming, is really very, very small. And the increased risk was mainly coming from changes in dynamical conditions, a combination of the stratospheric polar vortex, the timing of the breakdown of that, the sea surface temperatures over the Indian Ocean, and the sea surface temperatures over the Pacific Ocean, all three of which drove teleconnection patterns. And so these unusual dynamical states were represented in the atmospheric circulation, where the drawing from those is what drove the fire risk. And our knowledge about how such states might change in the future is highly uncertain. So because of this dynamical uncertainty, when you look at the precipitation maps that are projected by the climate models, you can see that it's quite a different picture than you get for the global warming. So in global warming, we have a certainty of warming, as I showed in the first slide. Here for precipitation, it can either increase, which is shown in the green colors, or decrease, which is shown in the brown colors. And you can see this is now for the latest models, the CMIP6 models, and this is the boreal winter season, cold season, and this is the boreal, that's on the left, and the boreal warm season on the right. You can see that indeed there's increased precipitation at high latitudes, which is very well known. And the stippling here, the full stippling is the IPCC stippling, which means the models are green sign. But we've also got a different stippling. This is a study from my group, open stippling, which characterizes where the models show large but non-robustly projected changes. This is something that isn't captured in the IPCC scheme. And you can see that these regions include many tropical regions. It's interesting that in CMIP6, the models now seem to give a consensus on wetting in East Africa, but that's still not really consistent with the historical behavior, and I'm not really sure. I'd be curious to think what the IPCC authors in AR6 think of that. In UK, though, you can see that we get, on the left panel, the wetter winters, and the right panel, drier summers. That's something that we know as the narrative for UK. But even where the precipitation projections are robust in sign, there can be significant quantitative uncertainty, even when you know the global warming level. In the case of Mediterranean cold season, Mediterranean drying, which is a very important climate hazard for Europe, because from a water security point of view, we in this paper we identified four different, we call them storylines of this drying, which are defined by uncertainty in the physical drivers of the circulation, which in this case were just two: the tropical upper tropospheric amplification of surface warming, that's a well-known climate feedback, and the change in the strength of the stratospheric polar vortex. And depending on those play out, you could get drawing mainly in the Eastern Mediterranean or the Western Mediterranean, or both, or neither. Here's another example recently from my group, where we look at the accumulated precipitation in cyclone clusters, or how that's going to change. That's a major cold season hazard, because as we know in Britain, the flooding often comes from not just a single storm, but a series of storms in the same place. So this is shown in the accumulated precipitation. And it turns out to be explainable from pretty much completely from a combination of the change in the number of cyclones in the cluster, which is shown below in the middle row here, and the change in the precipitation per cyclone, which is shown at the bottom. So the precipitation per cyclone, you can think of it as a thermodynamic effect, and you can see it's pretty much insensitive to, these are two different storylines, original change defined by the circulation. But the middle panel is you can see that it's a decrease everywhere, and depending on, except in Britain still gets probably more cyclones, unfortunately. But in Central and Southern Europe, you can see that there could be quite a strong decrease in the number of cyclones in a cluster, or a more moderate decrease. And depending on how that plays out, it means that in this part of the continent, the change in the accumulated precipitation extreme is uncertain in sign. So when you have a lot of uncertainty, you have to think of how you're going to approach decision making. This is a paper by Andy Sterling from 10 years ago, where he was talking in quite general terms about how you deal with uncertainty, and talked about whether the possibilities are unproblematic or problematic, or just the probabilities are unproblematic or problematic. So the upper left corner here is where you can really, this would be called the Knightian risk, where you can really quantify the uncertainty in a probabilistic measure and do a risk analysis. But I think it's fair to say for physical aspects of climate change, we're also dealing with this, we have to worry about the probabilities. We probably don't have to worry about possibilities as much. So we're down in this lower left part of the quadrant, and Sterling talks about how political pressures tend to push attention from the lower right part of the matrix, which he would call plural conditional states of knowledge, to the upper left, which is singular definitive states of knowledge. And we have to resist that if the knowledge isn't there, and on the other hand, find a language for expressing this plural conditional state of knowledge. So I know I'm supposed to talk about future events, but we always think of the future, or we often think of the future, of course, in terms of the past, which are important benchmarks. And in the case of the Thames Valley flooding in early 2014, it's still an important reference point. The observational record here shows for 140 years or so, shows that there was really an unprecedented event. The approximate explanation was a stuck jet stream, and there have been some studies on this, but there's really no accepted view on whether this is more or less likely under climate change. But what you can do is you can lay out essentially a causal network of all the different factors, including climate change and variability, and propagate that through all the way to climate impacts. And you can then construct different storylines or causal accounts of the event, and think about how future events might look. And this is something that we talk about in this paper. It provides a way to represent complex environments and adaptation options, bringing meaning to the climate information. So finally, just to say that many aspects of increasing hazard from climate change are anchored in basic physics of climate change, and are thus highly certain in sign. We know it's going to get hotter in certain aspects of precipitation. We can be very confident about sea level, of course. There's certainly enough knowledge to motivate action on mitigation. But for adaptation, there are still many uncertainties. All rare events essentially are shaped by dynamics, and changes in dynamical conditions are quite uncertain. This is especially crucial for compound events. In many regions of the world, especially in developing countries, even precipitation changes can be uncertain in sign. And of course, precipitation is a really, really important climate variable, so this makes adaptation especially difficult. Certainly, if warming gets above 3 degrees C, we are increasingly into uncharted territory, and the chance of tipping points in dynamical behavior increases. We're not just close to our current state. And climate models, it's fair to say, are far from realistic enough to provide confident answers here. So we need to find ways of exploring the uncertainty space in a meaningful and useful way, and I argue that storyline approaches offer a framework for doing that. Okay, thank you.